Okay, good morning, everybody. So, I'll talk today on a parallel implementation of device-independent protocol for quantum key distribution. And this is a joint work with Carl Miller and Yaowen Chi. And the paper appears in the archive. Okay. Right. So the usual implementation of a device-independent protocol for quantum key distribution typically goes as follows. So we have two parties, Alice and Bob, and they have two devices. What they do is they have some buttons in these devices that they press, and so essentially they input some classical bit strings and using these devices, which potentially share, let's say, some entanglement between them, they get output some classical bit strings. They have this raw key bits that they generate, right? And then they do a classical post-processing on that, okay? And for this classical post-processing, they use a classical channel, which is, say, a trusted classical channel. It's trusted. I mean, it's trusted, meaning it is noise-free, but it is accessible to the eavesdropper. Okay. So this is broadcast channel, and then they do some processing, and at the end they are able to obtain some final bits that they share between themselves. Okay. So this is the usual sort of the format in which such protocols work. Okay. Now, all right. So, as usual, like in cryptography, we always want to ask, what are the minimal assumptions with which we are working? Pardon me? Oh, sorry. Okay. All right. Maybe I'll try to not use it. Okay. So, in cryptography, the usual assumption so the usual question that we always want to ask is, what are the minimal set of assumptions that we are working with, right? So currently, like for most protocols, the assumptions are, of course, we don't want information leakage from Alice's lab to Bob's lab, right? So that is one assumption that we always work with. And then another important assumption, which is used in sequential protocols, is that the inputs that are generated are sequential. Okay, so this is an important assumption. The thing is that let's say that there is suppose Alice and Bob are interested in generating several bits, right? Several random bits. So what they will do is they will press some buttons on their devices and get some outputs, and then the next round, right? The next round that they do, the input that they put to the devices has to be independent of the output of the previous round. Okay? So this is very important in current protocols. That the next input is independent of the output of the previous round. Okay? So this requires a certain amount, certain sequential assumption. And also, there is a certain security assumption needed inside the lab, right? That is, somehow we are able to generate a new coin, a fresh coin, which is independent of the output. So whatever is going to be our source of the fresh coin, right, somehow should not get correlated with the current output. So this is a kind of a assumption that we need even inside our lab. Not just that we're not communicating across the labs, but also inside the lab we need this kind of assumption. So this is the assumption essentially that we want to get rid of, okay? We want to say, okay, that we can just generate all the inputs at the same time and enter all the inputs to the device, okay? And that we don't no longer require this assumption that subsequent inputs are independent of previous outputs. Okay. Right, so no need for instantaneous input generation. This can potentially simplify the experiment and also speed them up, right? Because Really no need to wait for this output to come out, then generate the next one, then wait, and so on. Okay, and we do get robust protocols. That is, they tolerate constant noise, and we also get constant key rates. Okay, constant key rates. So it basically essentially matches the parameters of current sequential protocols, except up to constants. The constants for sequential protocols are better. Okay, so what is going to be our usual attempt in designing such protocols, right? So what are we going to do? So typically we take some non-local game, right? So in this case we take this magic square game. So what happens in this game is that there is this, both Alice and Bob. So there is this 3x3 square that exists, and each cell in the square has a bit, okay? And Alice is given a random row number of this 3x3 matrix, and Alice is supposed to output the content of that row, okay? And Bob is given a random column number, and Bob is supposed to output the content of that column. And the further requirement is that that the overlapping cell value must match, okay? And that the parity of Alice's output, I mean the row, must be even, and the parity of Bob's output column must be odd. Okay? So of course this is impossible, right? This is not really possible. So therefore, Alice and Bob cannot win. So classically, they cannot win with probability 1. So the maximum success probability is 8 over 9. But quantumly, like magically, okay, that's why it's called magic square game, the success probability is actually 1, okay? So if Alice and Bob are allowed to share some entanglement between them, then they can actually achieve success probability 1. All right, and this game is known to be rigid. So rigidity implies that, like whenever the success probability of this game is near optimal, so in this case near 1, then Alice and Bob, so the whole thing is Alice and Bob are exactly doing what they're supposed to do, they're sharing exactly what they're supposed to share, and so on and so forth. So it's like the only way they can achieve probability near 1 is that everything is going exactly as planned, okay? All right, yeah, so in this case, if there's success, then because everything is as planned, they're sharing EPR, and if in case they're sharing EPR, it is uncorrelated with Eve, and therefore, the output bit, which is the common bit of the intersecting columns and row, is the shared key, right? So that's the key. Okay, now parallel QKD. Okay, so what are we going to do if we want parallel implementation, right? So we're going to input x1 through xn and y1 through yn in parallel, okay? And then we're going to output all the answers a1 through an and b1 through bn. Okay, now one thing that was important to see if in the game, right? If you see, in order to output this common intersecting bit, Alice and Bob need to exchange their row and column, right? Because this is really the intersection of the row and column, right? So they really need to exchange their inputs actually, okay, in order to output the bit. Now, so if we try to do that, that is they share the inputs, right? Then the Eve who's sitting on the channel will get to know their inputs x and y, right? And therefore, and then of course after that they will have to check that their magic square, that they're winning the game. The magic square condition is being satisfied on most of these instances of these games. So they'll do a random check on some large enough subset, right, to check that they're actually winning. And if they're not winning, of course, on the subset, they will abort the protocol. And then after that, the typical thing then would be to do is privacy amplification and so on. Okay. Right. So what we really want to say is that Eve's success probability in predicting the output of Alice, right, A1 through AN, is exponentially small in n. Okay, if it is exponentially small in n, then, so to say, the min entropy of A1 through AN given Eve is linear in n, okay, which then can be extracted out using Price equation. Okay. So the natural thing to do is, design this three-party game, right? Alice gets the input x1 through xn, Bob gets the input y1 through yn, Eve gets the input x1 through xn, y1 through yn. Alice has her output, Bob has his outputs, and Eve does these outputs k1 through kn. And the correctness now of this game is that Alice and Bob are winning the magic square, and Eve is able to predict the values of A1 through AN. So K1 through Kn is actually equal to A1 through AN, right? And this is the game, and we want the success probability of this game is exponentially small in n. Now, so typically, in order to do this, to try to get success probability exponentially small in the number of repetitions, we use these so-called parallel repetition theorems. So what happens is that in a parallel repetition question, so let's say we have a game, right? Let's say CHSH, whose success probability is 3/4 for one instance. And then if you play this game twice, actually what happens is parallel repetition, like the perfect parallel repetition fails. That is, you do get a success probability which is more than 3/4 square. So it doesn't go down, right? But this is only true sort of up to constants in the exponent, okay? So ran using, so of course the question is this possibility was that, that the parallel repetition actually fails, and then, for n parallel repetitions, maybe the success probability doesn't go down exponentially in n, okay? But ran using very nice information theoretic arguments showed for classical games that parallel repetition actually holds, and the success probability actually goes down exponentially in n. And later, for the quantum world, several such results have come out. We still don't have parallel repetition, perfect parallel or an exponentially decaying parallel repetition for all games, but they have been there for several successive classes of games. And what we use is the so-called free games, where the input is independent of, where the input to the two parties is actually coming from an independent distribution, right? So input x is independent of y. And then also Thomas uses another parallel repetition using so-called anchored games, okay, to arrive at the same result. Okay, so anyway, continuing with free games. So right, so typically in parallel repetition argument, what is argued is that if we condition on success on previous rounds, then the success in a subsequent round is pretty much what you want, omega of g, except it's perturbed a little bit, let's say order 1 over square root n, okay? And that is because the information that is leaked, about the subsequent round on the condition on the event of success on previous rounds is something like order 1 over n, okay? So anyway, these are some technical arguments, but using that, eventually what is shown is that if there is a subset S of size which is like linear in n, so constant times n, then the success probability there is as you expect, pretty much omega of g plus a little bit delta to the mod S, okay? But then it is important that S is only like epsilon times n. We cannot, in these arguments, make S go all the way up to n, or like 1 minus epsilon times n, okay? So this is important. All right. So now, okay, so we had this 3-player game. Okay, so of course, the first problem that we face is this is not a free game. The input to Eve is the same as input to Alice, right? Or has basically both the inputs of Alice and Bob, in fact. So this is not a free game. So one way to do that is to just not give any input to Eve. Let Eve output even the candidates for x1 to xn, y1 to yn. so everything remains as before. In addition, Eve's output should match Alice's input and Bob's input. So of course, for this, the success probability will be very tiny, right? Because there's already you're losing by asking Eve to guess Alice and Bob's input. So there's an additional 1/9 hit you will take. But then that's fine. Yeah, but as I said before, we cannot make it go all the way up to 1/9 to the n, right? Because we cannot let the size of S to be exactly n or close to n. It has to be epsilon times n. Okay? So that's what it is. So we take this S, which is of size, which is a random subset of size epsilon times n, and that's where we can show that the success probability is actually 1/n, roughly like 1/9 to the mod S. 1/9 is the probability for Eve to guess Alice's input in one game, Alice and Bob's input in one game. And then the success probability of the magic square is anyway 1, so that doesn't hurt. Okay. Now, how much time I have? Okay, how much time I have? 5 minutes? 5 minutes? Okay, all right. Okay, so let me just quickly mention like this, one thing which is sort of not super necessary in the proof, but nonetheless we use it, and it's something that is potentially useful. So basically, whenever there is, so many times we encounter this scenario where we have this like a party Alice, which is sort of making some measurement to get a classical output from her quantum system. So let's say a classical output X. And then there's an Eve which has the purification of this quantum system, and Eve is trying to guess this X, right? So Eve has an output E. And then we are asking what is the sort of the randomness left in X given E, okay? So usual measure is min entropy, but min entropy and this RenV2 entropy are anyway kind of closely coupled, so we can even ask about RenV2 entropy. And then so basically, what is this sort of the worst operation that Eve can do, right, for her best guess of X? The thing is that basically, approximately, one can say that the best that Eve can do already is this mirror measurement, right? So in the sense that in order to achieve H2, basically what Eve can do is, Eve can do exactly what Alice is doing, right? So Alice did some measurement on her part to obtain some output X. Eve has purification, so Eve does exactly the same as Alice and outputs, does the same measurement and outputs that. And that's going to be her best guess of what Eve's output is. Okay, so this is what we call as a mirror Eve, mirror measurement, etc. Okay. Now, and also there is one more technical part to take care of the robustness of the protocol. So if there is a little bit of tiny errors, even for an honest implementation of the protocol, we need robustness against that. So there's another little bit of technical argument, but I can skip all of that. And then we basically get so eventually it becomes a 6-pair game, but that's fine. Magic, UKD, yeah. Okay. Right, so the eventual protocol is like that. Alice and Bob play this magic square game n times in parallel, right? And they share inputs on a random subset of size epsilon times n, and then they also check correctness of magic square predicate on another subset, smaller subset of epsilon square times n, and they abort if the success is not at least 1 minus epsilon fraction of them. And if it does, then they record the outputs and discard the rest. We do get the statement that we want, which is H main delta is at least linear in n, which can be then later used to get linear number of bits using privacy amplification. So these are the technical things that we use: magic square game, the parallel repetition argument, the mirror adversary, and some other borrowed randomness stuff. Conclusions. Yeah, so of course the things that we use is Bell equipments are untrusted. A public classical channel is trusted, I mean, in the sense it's noiseless, but it is, of course, broadcast, so Eve hears about it. But the private randomness that each player can generate is really private, that Eve doesn't have an idea about that. So that's another assumption. And of course, that the information is not leaked between Alice and Bob, between their labs. Okay, so that is it. All right, so then of course, now the natural question is, can we use such parallel arguments to either simplify or help in any manner the current sequential protocols, say for random expansion or other tasks like universal quantum computation. Okay, thank you.
Any questions, comments?
Sorry, I'm not sure if I'm misinterpreting something you mentioned earlier at the start of the talk, but in terms of the inputs to the devices, is there some kind of restriction on how the input should be, in the sense a min entropy constraint of some kind? Because in the sense it can't be completely...
No, the inputs are uniform.
Okay, so the inputs are all uniform,
Yeah.
and input in parallel. Okay,
Yeah,
thanks.
yeah. Inputs are uniform and inputs are uniform and independent.
Okay, thank you.
Yeah.
So I'm just wondering how your rates compare to the sequential protocols, because you're assuming still that there's no information leakage from the lab. So I don't see why you can't assume there's no information leakage from the seed and then still do a sequential protocol.
No. See, the information leakage for sequential protocols is required within the lab, right?
Yeah, but you're assuming that you can do that anyway. So why can't you partition the lab as well?
Oh, partition the lab?
Yeah.
Okay, if that is something that... also, there is this issue of waiting, right? You have to wait for the output to come out, and then then generate like pretty fast the next input and so on.
Yeah, but I feel like...
And how many partitions are you going to do? I mean, this is n, right? N is large. So how many partitions are you going to do?
Well, you only need one partition. You can generate the seed, put it in a secure part of the lab, and then take one bit at a time.
Yeah. But the outputs have to remain independent of the seed then.
Yeah.
Okay, so
I
it
mean-
depends on the implementation, really. Yeah.
Yeah, okay. Thank you.
Okay, we are now already behind schedule, so let's not speak again and next to the next speakers.